Okay, we'll go ahead and get started today. Welcome everyone to our ACI Insight series. My name is Andrew Stinson. I'm a senior consulting engineer with Firefly. Today we're going to be talking about ACI and fabric forwarding um, within our ACI environment. And give me a second to get everything up here. My voice, I'm fighting seasonal allergies and cold, so definitely sounds much worse than it is. All right. All right. ACI fabric forwarding, and before we dive that, we need to lay some um, foundation first and a couple of refreshers about some other technologies. The first thing I wanted to establish early on is that in ACI, when we're dealing with at the network level, we're really the ACI environment actually acts like one giant switch. So if we take a look at, say, a Nexus 7K, like we're going to have some components on that switch. We're going to have our line cards, and our line cards are where our endpoints are connected to, right? We're going to have fabric modules, and that is what's interconnecting all of our line cards to each other. And then we're going to have our supervisor. Our supervisor cards, that's where we're running, say, an XOS through the CLI or maybe the API. And this is where we're making our configuration changes. And we connect to our supervisor card, we make the configuration changes. And that change is then translated into what's required to allow the endpoints to connect to each other. We don't see this lower level configuration. It just works for us. If we have an endpoint connected to this line card, an endpoint connected to this line card, assuming the same, well, just by default, when we connect them, they're going to have connectivity to each other, right? In ACI, we have a very similar scenario. Our supervisor, that's our apex. So our apex are where we're going to be configuring our fabric. We tell the APIC what we want to happen, and it translates that configuration and pushes it out to the fabric for us. The fabric module that's providing the interconnectivity for our line cards in our ACI environment, you can look at those as the spine. And then our line cards will be all of our leaf switches. So they're all interconnected to our spines. And by default, from a network level, endpoints within our fabric are going to be able to reach each other. Okay? So we'll kind of revisit how that works in our fabric later on. Next thing we want to do a quick refresher on is on VxLAN. So to talk about VxLAN, we're going to build a legacy network here. We're going to have switches 1, 2, and 3. We're going to have them connected to each other. And then we're going to have endpoints A, C, and B. A has address of A. And so we have these 3 endpoints, and in our legacy network, we're going to be running a spanning tree, right? So we have a loop here. So spanning is going to block one of these links. We'll say 2 to 3 is being blocked. Okay. So in this scenario, if we want endpoint A to communicate with endpoint C, the basic forwarding on our layer 2 network is going to follow this path. A wants to talk to C, so it's going to check its local endpoint ARP table, or its local ARP table, and see if it knows the address for C, the MAC address. If it doesn't, then it's going to do an ARP request. And that ARP request is going to have a source of host A, and then be the broadcast MAC address. Okay. That request goes to switch 1. Switch 1 is then going to learn that A is connected to, say, port 2. So it learns the MAC address for endpoint A. Now it's going to see that that ARP request has a destination of the broadcast. So it is going to flood that request out of all of the local interfaces. Okay. And we'll go ahead and add that all of these are in the same VLAN. We'll do VLAN 10 for everything. Okay. So that ARP request is going to be flooded out all of the local interfaces that belong to VLAN 10. It's also going forwarded to and switch 3. Switch 2 is going to learn about endpoint A, so it's going to learn that MAC address, and it is going to flood that request out of all of the local interfaces belonging to VLAN 10. B is going to receive that, and then it's going to just drop it. It's not intended for B, so it's going to ignore it. 3 receives that request. It learns about point A, and it floods out of the local interfaces belonging to VLAN 10. Endpoint C receives that request. It sees that it is intended for itself, so it is then going to reply. So C is going to send a unicast packet back to A, and the source is going to be C, and the destination will be A. When that packet hits, or that frame hits switch 3, then switch 3 is going to learn that C is connected to it. It knows where A is, so it's going to forward that over, which will then forward down to A. Okay? Standard layer 2 forwarding. Now, if we come in and make a change here, and we're going to say that these different VLANs. Okay. Now, these are still in the same subnet, but we've now got them in different VLANs. So will traffic still flow from A to C in our layer 2 legacy network? And the answer to that's no. Because they're in different VLANs, when we do our ARP request, gets flooded of VLAN 10, it's going to be the same thing with the other switches. They're going to flood out VLAN 10, and so C will never become another VLAN. Right? So VLANs in our legacy network is a layer 2 construct. and it is our flooding boundary. Now, in our traditional network, there's also a link between VLANs and our routing infrastructure, because we can have multiple subnets within the same VLAN, but we cannot have multiple VLANs within the same subnet. Okay? So here we have different VLANs here, same subnet. We don't have layer 2 reachability. So this structure here will not work in our traditional networking environment. Okay? This setup breaks ARP. And this is the main difference between our traditional network and a VxLAN topology. In a VxLAN topology, the VLAN does not define our layer 2 boundary. It does not define our flooding structure. It defines the ownership of a VxLAN segment. So the rules of what we understand a VLAN to be will change within our fabric. Okay? In our ACI infrastructure, we can have this setup where we have multiple different VLANs, endpoints in each of these different VLANs within the same subnet. We can still have layer 2 adjacency between them all. Okay. So when we talk about VxLAN, VxLAN is an encapsulation. Like our VLANs, going to have an ID number. For our VLANs, it was a 12-bit, so we have maximum 4,094 possible numbers, some reserved. For VxLAN, it's a 24-bit ID, which gives us 16 million possible IDs. Those IDs, you'll see them referenced as a VNet or a VNI, or it could be VNID. You can also see them referenced as segment or a VxLAN segment. Okay. These are all the same thing, the ID of that VxLAN. Okay. So in VxLAN, we're going to take the original payload and we're going to encapsulate it with a VxLAN header. And this is an 8-byte header. And that header is going to include the VNI. That's then encapsulated into a UDP packet, which then gets our IP encapsulation and then our Ethernet encapsulation. Okay. So the original source and destination IP and MAC address are all maintained within the original payload. Okay. These Ethernet headers, these are going to be referencing what's called our VTEPs. Okay. So we'll see what we're talking about with those when we talk about VTEPs. Those are the devices that are encapsulating and de-encapsulating the packet with VxLAN. Okay, they're the tunnel endpoints. They're going to be our switches. There'll be specific interfaces defined on those switches. Okay. Because we have IP in our header, then we need IP connectivity between our switches within our fabric to communicate with each other. And so, in order to accomplish this, we do away with spanning tree, and we're going to have a layer 3 underlay. So in traditional VxLAN fabrics, we have two different flavors of behaviors. We've got flood and learn, and we've got VxLAN routing. We'll cover each just briefly, and then we'll talk about how that pertains to our fabric. So we're going to draw our network out here again. So we have switch 1, 2, and 3. Endpoint A with VLAN 10. Endpoint B with VLAN 20. And C with VLAN 30. And then we'll have our IP addresses here and our MAC addresses. Okay. Now, we're going to have the links the same, but because we have an IP underlay, we can take full advantage of all the links. We can use equal cost multipathing. We're not going to have a link in block being blocked by STP because we're not running STP within our fabric. Okay. Now for flood learn, we're going to be running multicast, so IGMP v3. Okay. This is our new topology. And so we're going to be running layer 3 underlay. So we have IP reachability between all switches. So we're going to have loopback interfaces defined on all of our switches. Okay. And then we're going to define a new type of interface called an NVE interface. That's a network virtualization endpoint interface. And we're going to find our different VxLAN segments. Okay. Now, when we define our segments, we're going to go to switch 1, and we're going to create an NVE interface. And we're going to say that we are going to map our source interface to loopback 1. This is the logical interface where we're going to be encapsulating and de-encapsulating our VxLAN packet. And then we're going to map the VNI with our multicast group, and we're going to be doing some map with our VLANs as well. So in our VLAN, we're going to map, say, VLAN 10 to segment 10,000. Okay, so our VNI 1000 on the switch is going to be mapped to the local VLAN of 10. In our NVE interface, we're going to say that our segment 10,000 is going to be mapped to our multicast group. Say that group. Okay. We're going to head over to switch 2, and we're going to say that VLAN 20 to VxLAN segment 10,000. And we're going to have an interface that says that segment 1000 is going to be mapped to our multicast group. And the same thing for switch 3. I'm going to say that VLAN 30 is mapped to VxLAN segment 10,000. And our NVE interface is again mapping segment 10,000 to our multicast group. Okay. So when we want A to talk to C, what happens here? Well, just like before, the endpoints are going to behave exactly like they did in our legacy network. It's going to check its local ARP table, see if it knows C. If it doesn't, it's going to do an ARP request. Okay. And that ARP request is going to be a source of A, and destination will be our broadcast MAC. And it's going to go to switch 1. Switch 1 is then going to see that packet come in. It's going to learn that A is connected to it. And it sees that it's a broadcast. So it is going to flood that ARP request, the local interfaces that belong to VLAN 10. It's then going to encapsulate that original packet into a VxLAN packet with that VxLAN segment of 10,000, which is what we defined up here. My source is going to be my loopback 1 address defined here on my switch. Okay, that's my source interface on my MVE configuration. And my destination is then going to be my multicast group. The multicast group defined here for that VxLAN segment. That will then get forwarded through multicast to switches 2 and 3. 2 will receive it. It sees that it's coming in on segment 10K. It maps that to VLAN 20, and then will flood out of all the local interfaces that belong to VLAN 20, and Endpoint gets it and drops it because it's not intended for B. Switch 3 receives it. It sees that we have a mapping for VxLAN segment 10,000 to VLAN 30. So it will then flood out of the local interfaces with VLAN 30. C will receive it and respond. So when these packets are received by these switches, when leaf 3 receives that, it's going to learn that endpoint A is living on switch 1111. Okay. So when C responds, switch 3 learns that C lives there. It knows where A lives. It's then going to re-encapsulate that packet. It's coming from VLAN 30, so it's going to map it to VLAN 10,000. This will be a unicast packet. So now our source is going to be 3.3.3.3, which is our switch 3 loopback. Our destination is 1.1.1, switch 1, where A lives. And remember that within that packet, we have the original payload, which has the source of C and destination of A. Okay. That packet gets sent to A, or to switch 1. Switch 1 will receive it, de-encapsulate that packet, will learn that endpoint C lives, switch 3, and then we'll forward this original payload down to A. A will learn C's MAC address. Okay. So this can work fairly well, but there's a couple of issues with it. The first is that it's not scalable because there's no control plane. Anytime we're going to do a MAC or an ARP request, we're going to be flooding the fabric with that request. It's still multicast, but it's still additional packets going out. All of our broadcast traffic is all going to be going out through there. And as our fabric grows, then it's going to be more and more requests as more endpoints come online. There's also an issue if we have things like vMotion within our environment. So because no control plane that's tracking endpoints, if we had C move to switch 2, we're not going to get an update. So 1 is still going to think that C is on 3. So it'll keep sending packets that way until C until it times out and he sends another ARP request. Okay. So a couple of issues with the standard flood and learn VxLAN fabric. To resolve that issue, we introduce EVPN. So we have MPBGP and EVPN. Okay. So we're still going to have our IP-based underlay. So still no STP. Multicast, we're configuring BGP. And that's going to behave as our control plane. So we're going to set up BGP on all of our switches, and it'll be in the L2 VPN, EVPN family. And what that tells BGP is that in our BGP route updates, we're going to be learning the host MAC address, the host IP. We're going to be learning the VTEP. So we're going to learn the location of that host. And we're going to learn VNI, the VXN segment that host belongs to. Okay. So our configuration will be slightly different, and it will be bigger than the previous configuration. And we're going to have a couple of new VNIs created here. We're going to have a layer 3 VNI, so a layer 3 VXLAN segment. This is going to be representing the tenant VRF. Okay. And we're going to have a layer 2 VNI. And this represents our bridge domain that our hosts belong to. Okay, so this is our layer 2 broadcast. So when A sends traffic, switch 1, when it sends an ARP request, again, source is A, destination is C. Switch 1 is going to learn that A is connected, and it's then going to an update to all the other switches in the environment that lets them know that A is connected and what switch they're connected to. Okay. So when A sends that traffic, 1 is going to check its B table and sees if it has that information. So if C has joined in, then we're going to know that C is connected to our fabric. And so it can just forward that request directly to switch 3. So this makes it more scalable. And this is what we'll see in most environments that are running a traditional VxLAN fabrics. The benefit is when C moves, as soon as C sends traffic, there'll be a new update. And so all the other switches will get notified that C has been moved. Now, ACI works similar, but there's some slight differences. Okay. And we actually are
True.
able to take advantage.
There's one question.
Yes.
What about sleeping device like see was the printer? Then what will happen?
I'm sorry, you're breaking up really bad.
I'm asking. Suppose C was the printer. A printer is the sleeping device. What will happen?
If it's what in a traditional VxLAN fabric, or
Yeah.
we're,
Fabric.
if that port, if it hasn't been received an update, then there's not going to be but there'll be a layer 2 VNI configured for our flooding, so that our request could be forwarded through that layer 2 virtual network. If you want to go into more detail about traditional VxLAN fabrics, you can reach out. We can have a discussion on that. But we're usually data center, we wouldn't see something like a printer, but we will talk about silent hosts
Okay.
that will
Thank you
in
so
an
much.
ACI fabric case. Yeah, not in
Yeah.
a traditional VxLAN fabric.
Okay. Thank you.
Uh-huh. All right. So in our okay, so when we're talking about ACI, we're actually going to both flood and learn and the gateway or BGP routing within our fabrics. Now, instead of using BGP EVPN for the control plane, ACI will use, and we'll talk about Coop in a little bit later. Um, and we're also going to benefit from the flood and learn behaviors because we'll be running multicast for our broadcast traffic as well. So in our ACI environment, remember ACI fabric as one giant switch. From a purely networking perspective, all endpoints can reach any other endpoint. From an application perspective, traffic is blocked by default and needs to be allowed. Okay. So we're going to talk about some of the network constructs of forwarding first. So when we look at our fabric, we're going to have our spines and our leaves. Okay. Our leaves are connected to all of our spines. They have to be, but they should be. That gets us the most benefit of this spine leaf architecture. And when we're talking about this forwarding today, we're only talking about a single pod. I'm going to talk about multi-side or multi-pod or anything today in forwarding. If we take a look at our previous scenario, we've got endpoint A, endpoint B, and endpoint C. Okay. So the thing to understand that within our ACI fabric, single tenant, or if there isn't any routing within our fabric. So we'll explain what I mean by that. The hosts behave exactly the same way they would in a traditional network. So our hosts here, A, B, and C, have no awareness of the fabric existing, of anything going on, VxLAN existing, nothing like that. The hosts are going to behave exactly the same way as a traditional network. Okay. So in our scenario, if we wanted A to communicate with B, A is going to check local ARP table. If it has an entry for B, if it doesn't, it's going to send an ARP request. So the source for that ARP request will be A, and the destination will be our broadcast, exactly the same way, okay? That traffic is going to leaf 1, and leaf 1 is going to learn that A is connected to it, okay? Now, this is where there's a fundamental difference in what happens within the fabric. So there is something called an endpoint table in our leaves. And that endpoint table is going to have our MAC addresses and our IP addresses combined. Okay? So it's going to be keeping track of both of those. When it receives frame, then it's going to layer 2 frame, then it's going to learn the MAC address. If it receives an IP packet, layer 3 packet, then it's going to learn the IP address. Okay. Once the leaf learns about endpoint A being connected to it, it is then going to send a okay. All right. So Coop, this is the control plane protocol for ACI. This stands for the Council of Oracles Protocol. Okay. And Coop designates something called oracles, and those are our spines. And the citizens, those are our leafs. Okay. When a leaf updates the endpoint table, it is going to send a Coop join to the spines. Okay. The spines, when they set up your fabric, there's going to be a Anycast VTEP address created. And all of our spines have that address. So that Coop join is going to go to that address. Okay. When any spine gets that, it's going to update the Coop database. That's called the proxy table. Okay. And it's going to base endpoint A lives on leaf 1. If we know the MAC address or the IP address for A, then we're also going to have that in our table as well. So we'll have both MAC address and IP address if we know both of those for the endpoint. Okay. Once one spine gets an update, it will replicate it to the other spines. So all the spines have a full mapping and awareness of all the endpoints within our fabric. Okay. That traffic does not get forward, that entry does not get forwarded to any of the leads. It's just a join, say, hey, this has been added, and it'll just be added in the spines. Okay. There's one instance we'll talk about a little bit of that where the spines will actually send a message to a leaf to make an adjustment to the point table. But in general, it's a one-way message, just from the leaves to the spines. Okay. Okay. So back to our previous scenario, we have endpoint A that connects to send a ARP request to leaf one. Leaf one receives it, add the entry for that input to its local table, and then it's going to send a Coop join to the spines. The spines are going to update the proxy table, sees that endpoint A is connected to leaf one. Now, there's two different behaviors that we could see within ACI. I'll talk about the legacy behavior and then the new behavior. Before version 4.2, the default behavior was something called directed ARP. So with directed ARP, what would happen is that when leaf one receives that broadcast, it would the ARP request, and it will identify who they're looking for. So it would see that we are trying to look for B. And it would then look at its local endpoint table to see if it has an entry for B. If it didn't, then the traffic will be to the spines via the local, via the Anycast VTAP. Okay. And then the spines will receive that packet and it will look in its proxy table to see if they have an entry for B. Okay. So it's going to look to see if it has 10003 in its proxy table. If the spine knows what it is, then it's going to re-encapsulate the packet and send it to leaf 2. So we know that 3 is at leaf 2. So we're going to re-encapsulate the packet, and the source is going to be leaf 1, and the destination will be leaf 2. When leaf 1 sent this packet out, I forgot to mention that the VxLAN encapsulation, the source will be leaf 1, and the destination will be the Anycast VTAP on the spines. Okay. As soon as leaf 2 receives this, it'll de-encapsulate that packet. It will learn that A is on leaf 1. It will see that it is intended for 10003. If it doesn't have, if it's in the proxy table, then it knows that 10003 is connected to this port, and it will forward that request to B. B will receive that ARP request, the original packet, and it will reply with a unicast reply. That will be a source of endpoint B with a destination of endpoint A. Leaf 2 is going to look at that, sees that the destination is A. It knows that A is on leaf 1. So it's going to re-encapsulate that packet with the source of leaf 2, destination of leaf 1. I send it to 1, who is then going to learn that endpoint B is connected to leaf 2. It de-encapsulates the packet and then forwards the original payload to A. And we can then establish direct connection. The next packet or frame from A is going to go to leaf 1 and it'll go straight to leaf 2 because it already knows where B lives. Okay. All right. So in our
Hello.
fabric, yes.
One question. Means both spine will send duplicate packet to leaf 2, or only single spine will send the ARP request packet to leaf 2 where
Uh,
B is located.
the first spine that received it is going to forward the encapsulate it and forward the packet. It'll just be one packet. It won't be duplicate from all the spines.
Means switch spine 2 will not send the ARP request packet to leaf 2, correct?
So if the destination is unknown, it's going to go to the spines. One of the spines is going to receive it, look in the proxy table, sees that
Correct.
we know where it is, then it will re-encapsulate the packet and forward it.
That is okay, but my question is why spine 2 will not send the duplicate copy? Is there any mechanism who will send the packet to
Yeah,
another device?
there's some communication going on between the spines. So the first one that receives it is the one that delivers it. What happens is that there is there is going to be a spine that's going to be the owner of the specific entry on the proxy table.
Okay,
Okay.
okay,
They'll
got
all
it.
have copies of it, but one of them will be the primary or the owner
One
of
will
that
be
entry.
owner of that
Yeah,
entry, correct?
yeah.
And they will identified by the synchronization of the proxy database, correct?
When the database is updated, then the one that does the update, that's the primary one for that entry.
Correct. Okay, thank
Okay.
you so much, Henry. Thank you. Yeah.
All right. So within our ACI fabric, we have a combination of logic and this control plane behavior. So our control plane mechanism is Coop. So we don't have to flood our traffic. Okay. Now, in our fabric, we have the concept of our bridge domain. Now, I mentioned the bridge domain before when I was talking about a VxLAN fabric. And remember, that was in reference to our layer 2 VNI. So in ACI, we will see a logical construct called a bridge domain. And that is a combination of a VLAN segment and a multicast group. Okay. And this defines our layer 2 boundary for our flooding broadcast within our fabric. Okay. So VLAN, a traditional VLAN, is not our layer 2 boundary within our ACI fabric. A VLAN is just identifying membership to another construct that we have, which is our endpoint group, which is then linked to our bridge domain in our layer 2 VNI. Okay. So again, the VLAN is not our layer 2 boundary, our ACI fabric. Our bridge domain is layer 2 boundary. And that's a combination of a VxLAN segment ID or VNI and a multicast group. The bridge domain is also where we can change behaviors within our fabric. In the previous example, when I talked about directed broadcast, we had or directed ARP. We can disable that by enabling ARP flooding. If we enable ARP flooding, then instead of looking at the ARP header and forwarding to the spines for lookup, instead we're going to flood that ARP request to our other endpoints within the same bridge domain. This is one of the things we would do if we had a silent host, and that would ensure that they would receive that ARP request, and they should respond to the ARP request, which would then add them to the local endpoint table and then to the proxy the spines. Okay. Our flooding is enabled by default now on ACI, but you can turn that off. You also have the option of changing how our flooding behaves for our bum traffic. We can choose an option that says hardware proxy or flood. When we choose the hardware proxy, that means we're going to the spines, so we're going to do lookups for it, or we can just flood it through the fabric. Hardware proxy is the default option. Okay. All right. Okay, so for support of the flood and learn behaviors that we can take advantage of in our um, fabric, because there's no flooding natively within our ACI fabric, we use multicast. So it's going to be more efficient um, when we have that broadcast traffic. In ACI, there's a couple of terms I want to introduce here. The first is the GIPI address. This is a group inner IP address. And this is the multicast group that the endpoint is trying to join. So if we have native multicast traffic within our fabric, that's what the group is going to be termed as a GIPI address. Okay. So this will be in the original payload, be encapsulated in the original payload. Outside of that, what it gets encapsulated with is the GIPO address. So the group IP outer address. Okay. So the GIPO address, this is used for in all of our broadcast traffic and all of that within ACI. The GIPO address is used for multicast distribution across our fabric. It's allocated to all domains, okay, and any multicast enabled VRFs. By default, you set this range up whenever you set up your fabric. The default is 225/15. That's the default GIPO range. It can be changed. And the underlay separate from our tenant multicast groups. So we have two different groups for our underlay than we have for our tenants. Whenever we assign a GIPO address, when a bridge domain is created, it's going to give it an address. And so let's say we get .208 is the GIPO that's assigned. This will be a /28. Okay. The last four bits in are going to be used to assign what's called to choose an F tag. Okay. So with traditional multicast, is there a way that we can balance traffic for multicast with our ECMP? No, we don't have that ability. We have one interface where we join, and that's how multicast works. In ACI, we use a thing called F tags or forwarding tags to gives us the ability to load balance our multicast traffic. When we stand up our fabric, there's actually 16 tags in total, but 1 through 12 are usable, and they're assigned to our spines originally. So 1, 2, 3, 4, 5, 6, and so on. If we only have 2 spines, if we have 3 spines, then it's 1, 2, 3, 4, 5, 6, so on. Okay, so each spine will get an address, and it'll count up to 12 to assign them. If there's a change in topology, if we add another spine here, then it can be renumbered. So 3, 4, 7, 8, 9, and so on until reach 12. Now, when we had our GIPO address, okay, if we have multicast traffic or broadcast traffic that we're needing to send, the leaf is going to pick one of the F tags for that traffic. So A is part of this bridge domain that has this GIPO assigned to it. And we see we have these F tags assigned. So it's going to pick one of them. And this will be associated with the addresses 209 to 220. So if we look at the last 4 bits, then we'll see the bits, 12 bits that we have available line up to the 209 to 220 address. And so it's going to pick one. And so this address will be 209 because this is where F tag 1 is. And this one will be 210 because this is where F tag 2 is. So the first broadcast may choose this interface. And so this spine, or this tree, will forward the traffic. Okay. The next broadcast, it'll choose this interface, and this tree will be used to broadcast the traffic and the traffic out. Okay. So in this way, we can load balance our broadcast traffic within our fabric using multicast. Okay.
So in this situation, leaf is getting two packets.
I'm sorry?
So in this situation, leaf is receiving 2 packets,
Which
2
leaf?
multicast packets for same.
If these are 2 different broadcasts sent, and the leafs were uh, part of that bridge domain, have that bridge domain deployed, then leave both of those if those are in the same bridge domain. Yeah. But those will be
Okay,
2 different broadcasts that's happening. Yep.
got it. Thank you.
Uh-huh. Okay. So we'll draw out our scenario in here. So fabric, we have A, B, and then we have C. Okay. So we have our gateways deployed to our leaves. So in this scenario, we are wanting to communicate with C. Okay. So before we had A communicating with B and they were in the same subnet. Now we have A communicating with C, different subnets. So if A wants to send a packet to C, what's going to happen? Well, the hosts are going to behave exactly the same way it would in a legacy network. They know no difference. So A knows it wants to talk to 10.0.1.2. It knows 10.0.1.2 is in a different network. So it needs to ARP for its default gateway. So it sends the ARP for the default gateway. Leaf 1 will receive that request, and it will respond with its ARP, with its MAC. Leaf 1 learns that A is connected, and then it sends the Coop join up to the spines, and the proxy table is updated that A is connected to leaf 1. Okay. Now, leaf 1, now A will then send the packet to the gateway destined for 10.0.1.2. Okay. Leaf 1 will take that packet. It will encapsulate it just like before. Our source will be leaf 1. If it does not have an entry for 10.0.1.2 on the local endpoint table, then it's going to forward to the spine proxy. Okay. Okay. The spine, the spine VTEP. The spine is going to receive that packet, and it's going to take a look at the destination and sees if it knows where C lives. In this case, C is on 3. So it's then going to re-encapsulate that packet. The destination will be leaf 3. The source will be leaf 1. Whichever spine it was that it will then go to leaf 3. Leaf 3 learns A is connected to leaf 1, de-encapsulates that packet, forwards it to C. C will reply, which goes back up to leaf 1. So source will be C, destination is A. Leaf 3 receives it. Leaf 3 will re-encapsulate it with the source of leaf 3 and destination of leaf 1. It goes to leaf 1 where it learns where C is, de-encapsulates the packet, and forwards down to point A. Exactly the same behavior as if they were in different same networks, just because they're in a different ARPing for our gateway. Okay, but we can still have layer 2 reachability within our ACI fabric. It doesn't matter if they're in different networks because we're encapsulating everything within our VxLAN. Okay, and our VLAN is not our layer 3 boundary. Our VxLAN is. Now, one of the things to note about this behavior is that I have these gateways defined here. When you're troubleshooting endpoints in ACI, you want to start with the endpoint. And what you want to do is try to ping gateway. The fabric is hosting your gateways. You want to ping your gateway, and if you can ping your gateway from your endpoint, that means that a whole lot of your configuration is correct. You don't have to troubleshoot your physical configuration, the VLAN pool, your physical domain or VMM domain, your port group, if it's virtual, all of these different configurations, your interface profiles, and everything are all set up right. Your bridge domain is set up right. Your endpoint group is set up right. All of those things are right. And what usually is issue, and so you start troubleshooting your contracts. The other thing that might happen is if this endpoint can ping gateway but can't reach C, and you go to C and ping its gateway, you might be able to start pinging again from A because C just might not be like we talked about on a host. If leaf does a packet or a frame from an endpoint, that endpoint doesn't exist. So you're not going to be able to reach that endpoint until it's entered. Okay.
In this example, both subnet was the part of same BT, right?
Say that again.
In this example, both of the devices means both of the subnet is the part of same BT, right?
They're in the same rich domain, yes. Yeah, in this example. Uh, uh, in, possibly in the same endpoint group as well.
Okay, thank you.
They don't have to be in the same endpoint group. They could be in different ones, but yeah.
Okay, thank you.
So if you do have a silent host, there's a couple things you can do. One is you enable the ARP flooding. So any ARP requests will be received by that endpoint, so it should respond. If for some reason you have an endpoint that doesn't respond to ARP requests, um, uh, then a couple of things that you can do, especially if you have one that doesn't have a lot of regular communication, so it might time out, is you can go into your endpoint group and you can create what's called a static endpoint. So you can define the MAC and the node or the leaf and the port and the VLAN and IP address. If it's a layer 3 connection that you're using with, you can add the IP address in the endpoint group itself, and that will force a static entry for that silent host. Okay. One of the other behaviors we'll see is that inside our ACI fabric, if we're dealing with IP traffic, if A is sending a packet to C and the spine don't have entry for C in its proxy table, what's going to happen is a process called an ARP glean. So in an ARP glean, the first packet is dropped, and the spines are going to send a request to the leaves on its behalf to do an ARP request. And so the leaves will flood the ARP request through its ports. That should force C to respond, which will then add C to the endpoint table and cause a Coop join, which will then add C to the proxy table. And so the next packet that comes in will then get forwarded to the correct location. All right. Coop said that it's a one-way communication, and there was an instance where it could be uh, could communication from spines to leaf, and that behavior occurs when we have a endpoint that moves to a different leaf. So in this scenario, leaf 1 knows that A is connected to it, and it knows that B is on leaf 2. Okay. The spines in the proxy table knows that A is connected to leaf 1 and that B is connected to leaf 2. Now, perhaps a vMotion or something, and B moves to leaf 3. Okay. Now, as soon as leaf 3 receives some sort of packet or frame from B, it is going to, let me add on here, this knows that B is connected to it and A is connected to leaf 1. As soon as leaf 3 receives some sort of packet or frame, something from B, it's going to update its endpoint table and know that B is correctly connected to it. That's going to spawn a join to the spines. Now the spines are going to see that it already has an entry for B pointing to leaf 2. It's going to say that it is now connected to leaf 3. It is then going to push a change down to leaf 2 and tell it to add a bounce record that says that endpoint connected to leaf 3. Okay. Now it only goes to leaf 2 because that's where endpoint B was located. Now if A and B have been communicating, A is then going to send its next packet in. Leaf 1 is going to take a look at its local endpoint table, sees that B lives on leaf 2. Leaf 2 is going to receive that packet, look at the local endpoint table, and sees that B is not connected locally. It is connected to leaf 3 now, and it has a bounce record for that. So leaf 3 is then going to take that packet, forward it to leaf 3. Leaf 3 table to learn that A is connected to leaf 1. It will encapsulate that packet and forward it to B. B will respond. Leaf 3 will encapsulate it with the source of leaf 3, destination leaf 1. When leaf 1 receives that packet and it de-encapsulates it, it notices that what was received from leaf 3, not leaf 2. So it will then update its endpoint table to be the new location for that endpoint. Okay. All right. So when we're talking about our VxLAN encapsulation, know that for our layer 2 traffic, our encapsulation is going to be based on the VxLAN segment defined on our bridge domain. That bridge domains, that VxLAN segment is assigned automatically by the APIC whenever you create that bridge domain. Bridge domain, we will also have a multicast group assigned. That's our GIPO. Okay. Our layer 3 traffic, and you can say this is our layer 2 VNI. Our layer 3 traffic is broadcast traffic. is going to, or not just broadcast, but all our layer 3 traffic is going to use a VxLAN segment that's assigned to our BERF. You will also see context as a term in ACI when we're looking at our CLI will reference the context, but the VxLAN segment is assigned to the VRF. Okay. And that is the equivalent to the layer 3 VNI in our VPN. Our native multi-destination traffic is going to be flooded in the bridge domain. The VLANs are not our layer 2 boundary. Our bridge domains are our layer 2 boundary. So we can have multiple endpoint groups that are attached to the same bridge domain. They can have multiple VLANs assigned to them, and there can be multiple subnets involved. That doesn't matter. Our layer 2 boundary is our bridge domain. If they're all part of the same bridge domain, then we have layer 2 reachability. If our servers have broadcast traffic that is not ARP, then it will get flooded. And for our flooding, we're using multicast. Okay. All right. Questions around the forwarding? Okay. All right. Well, that ends this session for our ACI Insight series. If you join us on our next time, we're going to be talking about logical constructs within ACI. We'll be referencing some of these items that I've mentioned today: tenants, our VRFs, our bridge domains, our endpoint groups. We'll be looking at level, things like that. If there are no more questions, thank you everyone for joining us today. Hope good rest of your day.
Thank you. Thank you, Andrew. Thank you so much.
Sure. Thanks a lot.